and welcome you to this gathering and kindly enlighten us on spintronics.
Thank you, sir, for the warm welcome. Happiness radiates like the fragrance from a flower and draws all good things towards you. I now request Professor Vijay Kumar from Bangalore University to extend a floral welcome to Professor Anil Kumar. Now, Professor Prakash will welcome the chairperson, Dr. Chandrasekhar Shetty, with a bouquet of flowers. I invite Professor Mohammad Haroon, retired principal, Anjuman College, Bhatkal, to extend a floral honor to Professor Prakash Karat. I call upon Dr. Ravi from Honeywell, Bangalore, to welcome Father Pradeep Antony with a bouquet of flowers. I request Mr. Rajesh Kumar from Alvas College, Modbidri, to extend a floral welcome to Professor Lawrence Pinto. Thank you, sirs.
Topic, and we have very eminent person, an expert, to enlighten each one of us gathered here with keen interest. All that I wish that occasion like this only reminds us something that we can draw for ourselves from the topic itself. The word of spin electronics constantly reminds us that things are at change, constant flux. And with that keen interest,
in the past? No. Okay, good. Then it's easy. Let me rephrase my question. How many of you are using a computer here? How many of you are using a computer which is made after 1998? All of you. Okay, the good news is that all of you are using Spintronics, right? So today you will come to know where you are using Spintronics, and that's the purpose of this lecture, right? So we are using many things, but we should also know where we are using and why we are using. And also, I mean, in this kind of lectures, I just try to give a message to the students. You know, when students, especially after 12th, they have a confusion whether they should do science or engineering or medical. So often the question that comes to students is that, is there anything left in science to do, right? So as a physics student, you also may have this question, is there anything left for us to do, or whether I should do a PhD, because everything has been done, right? So that's the kind of a feeling students have. So I just remind them that, look, in 1899, the American patent officer said that all what is needed for the mankind has been invented. He looked around, he found bulb is there, electricity is there, motor car is there. So he thought that that's enough. So in 1899, he made a very bold statement. Look, what is needed for the mankind has been invented. Today, if you look back at that statement, such a foolish statement, right? And if somebody makes such a statement today, it won't take 120 years for people to realize that such a foolish statement. So we have not even done even what is the beginning of the science. So there's plenty of things to be done, right? So that's why the students have got enough opportunities in future. So let me give one quick example before I proceed further. All of you have studied photoelectric effect, right? So the photoelectric effect, for which Einstein, for the interpretation, Einstein got the Nobel Prize in 1905. He said that, you know, when photons of sufficient energy incident on a metal, electrons will be ejected instantaneously, right? So we all think that we understood photoelectric effect. So now the question is that, what is this instantaneous? What is the meaning of instantaneous? What's your feeling? how fast it is? Yeah, just speak. Let's have an interactive session. Huh? So people had this curiosity. So people started doing experiments. You shine with photons, look for an electron which is coming out. Within 1 second they looked at it, the electron is already there, so it's faster than 1 second, right? So then, as time progresses, every decade, the time resolution changes by 3 orders of magnitude. That's a trend which we are seeing. So then people shine with photons, look for electron which is coming in 1 millisecond, 10 power minus 3 seconds. Electron is already there. Then people are not stopping there. They went to microsecond time resolution. That means 10 power minus 6 seconds. So they shine with photons, look for an electron in 1 microsecond, electron is already there. So it's a pretty fast process, right? Then again, as 1 decade passes, people did nanosecond spectroscopy. That means you shine with light, look for an electron within a nanosecond. Electron is already there, right? So it's fast, pretty fast. Then, time progressed, 10 power minus 12 seconds. Because as time progressed, femtosecond spectroscopy, 10 power minus 15 seconds. You shine with photon, look for an electron in 1 femtosecond, within 1 into 10 power minus 15 seconds, electron is already there. So it's pretty fast. So now this is the age for attosecond spectroscopy, which is 10 power minus 18 seconds. So people now shine with photons, look for an electron in 1 attosecond, which is 1 into 10 power minus 18 second, the electron is not there. Right? Waited. 2 attoseconds, 3 attoseconds, 5 attoseconds, 10 attoseconds, electron is not coming. Then we found that few tens of attoseconds, after that electron is coming, right? So now the question is that, why is such a slow process? What the electron was doing for such a long time? Whether the photon is going in and doing some other business for that electron to come out, or the photon has knocked out the electron, whether he is doing some other business before coming out, people are curious now, right? So the thing which we thought that we understood, photoelectric effect itself, after 100 years we find that no, we have not understood, because the process what is happening inside we don't know, right? So now, after maybe a decade, you will have 10 power minus 21 second spectroscopy. That time we will invent many more things what this photon is doing inside and electron is doing. As quantum mechanics teachers and as a quantum mechanics student, I had this puzzle all the time. Teachers will tell that electron is disappearing from here and appearing there. So we ask the question, transition from one state to the other state. What happens in between? It's instantaneous. So now you don't know. Even the quantum mechanics, as time progresses, we may see that there are many more processes that are happening. So in that sense, this is an open-ended area. So many things. This is a simple example which you thought about photoelectric effect, which you think that you understood, right? Now the question is that, was Einstein wrong? Because he made a statement, it is instantaneous, it's not instantaneous, it takes such a long time. So he was not wrong. Prior to 1905, people thought that the energy means intensity. As more and more photon comes, more and more energy. That's what people were thinking at that time. So Einstein said, no, it's not like that. Even a single photon can knock out an electron if sufficient energy is there. So that is the reason he said, no, you don't have to accumulate many more photons before an electron is knocked out. It's an instantaneous process. He never had time in the mind, right? Instantaneous means a photon will knock out an electron. You don't have to wait for all photons to accumulate so that it gathers enough energy and knock out an electron, right? So Einstein is right. He never thought about time as the process for instantaneously, right? So I'm just telling you this because this is an open-ended question now. So many physics students should be doing this kind of experiments in future to understand what's happening, right? Okay, with this, let me start. So this is my research group. So I work on different areas of current matter physics, and these are the PhD students currently doing PhD under my guidance on those various topics. So I have some postdoctoral fellows, inspire faculty members, and many project assistants, UG students, etc. So they work on different aspects of magnetism, topological matter, spin-polarized electron scattering. These are some of the labs which we have on all these things. Now coming to the main topic, spintronics. So what is spintronics? Spintronics means spin-based electronics, right? If you consider an electron, You know that the electron has got a charge, electrical charge of the electron. The electron has got a spin. So you have a spin and a charge for an electron. And when you talk about conventional electronics, you worry about only the charge of the electron. When you talk about a diode or when you talk about a transistor, you only make use of the charge of the electron, right? So you don't worry about the spin of the electron. Now, today we started worrying about the spin of the electrons, so along with the charge. So that's why it is called spin-based electronics or spintronics. When the area started in 90s, it was known as magnetoelectronics, but the name was not very fashionable. So then we thought, okay, people thought that, okay, it's a good idea to change the name. That's why this spin-based electronics or spintronics has come in, and that has become very popular. It's not that it became just popular, it's an important area, right? So if you look at spintronics today, I mean, this is the status of electronics in 1960s. When the electronics started in 1960s, it was part of physics department. Now you can see Department of Electronics separately. I won't be surprised 10 years down the line if you have a department of spintronics, because the kind of application potential of this area is enormous. So where is the uses of this spintronics is coming in? So if you look at the spintronics materials technology here, you see different people contribute to the spintronics material technology. Physicists, chemists, material scientists, computer science, all the people contribute together. And what is coming out is interesting. So you can have speed sensors, location sensors, angle sensors, etc. So the spintronics technology allows you, I mean, let me just start with one small thing. Okay, maybe the sensors is one part. The data storage, which is the one which I was asking about, who is using a computer, so I'll discuss that in detail later. Then something called magnetic random access memory. The next one is the next generation spintronic devices, which is spin FET, spin memory, quantum computing, etc. So now look at this sensors, magnetic field sensors. Spintronics allows you to get very good quality magnetic field sensors, right? So what is a magnetic field sensor? Suppose if I have a magnet, and if this is a sensor, so this sensor senses this magnetic field. Now, the quality of a magnetic field sensor is defined by the fact that how far you can take this sensor away from the magnet, still I am able to sense this. Since still I am able to sense this magnetic field. Now the question is that even more efficient means I make the magnet smaller and smaller and smaller. Still at a far away distance, I am able to sense this magnetic field. Then it's a very good quality magnetic field sensor. Spintronics allows you to make good quality magnetic field sensors. So now the question is that if I have a magnetic field sensor, where can I use it? The sky is the limit. Imagine that you are bicycling and you keep a tiny magnet on the on the rim of your bicycle and a small magnetic field sensor on the fork. And when you bicycle, you bring this magnet close to the magnetic field sensor, it gives a signal. Then when you move further, in the next revolution, again it comes close to the magnetic field sensor, so it gives a signal. Now the total distance traveled is 2 pi r. And the time between these two is delta t. 2 pi r by delta t gives you the speed. So that means for each revolution, you get the speed of your bicycle, right? A contactless method, those who are riding a bike with a speedometer cable where the cable breaks frequently, you understand the difficulty. Now imagine that, just a contactless way of finding out the speed of a bicycle for every rotation. Now imagine that I have an accelerator in or the steering wheel, right? So there's no connection between the steering wheel with the rest of the car, imagine. And in the steering wheel at the bottom, you have an array of magnetic field sensors and a magnet below that. When this steering wheel rotates by 1 degree, the sensor realizes that there's a 1 degree rotation, send a signal to the motor to rotate the tire by 1 degree. And like that, a contactless way. So that means you can rotate your steering wheel with a little finger. There's no contact, there's no bearing. So, and also imagine that you wanted to give the acceleration. So the pedal is like this, and when the pedal moves in, so there's an array of magnetic field sensors that senses this the position of the pedal. So as you keep pressing the pedal, you know the location of the pedal, you know how much degree it has gone in, give a signal back to the fuel injection system to inject more and more fuel. So it's like a contactless method. Another interesting thing, look at this door. I want to open this door, right time. I want to open this door. Imagine that I kept a motor on that door, right? And I switch on the motor rotates, the door opens. And now the door opens and comes close to the wall. If I don't switch off this motor, this door will come and bang onto the wall, right? Now imagine that on this door I kept a tiny magnetic field sensor and a magnet on the wall. So this door opens, comes close to this. When these things are very close to each other, the sensor gets a signal. That signal is given back as a feedback loop to the motor, stop. So the door just opens and stops there, right? It has become a position sensor. Previously it was a speed sensor, now it's a position sensor. Now imagine that while this door is opening, at every 10 degree I keep a magnetic field sensor. So at every 10 degree I get a signal. Then I know the door has opened by 10 degree, 20 degree, 30 degree, 40 degrees. It's become an angle sensor, right? So it's your imagination that stops you where you can use this magnetic field sensor. If you take a modern car, there are more than 35 magnetic field sensors for different purposes. And the quality of the sensor is getting improved day by day. Earlier days it was not possible because if you need 1 kilo of a magnet which is sitting on the rim, it's too heavy. Nowadays bicycle itself is weighing 3 kilos to 5 kilos, right? So the development of this Spintronics has allowed this kind of technology to come in, right? So now let me just talk about the magnetism that is used in this Spintronics. Suppose if I have a ferromagnetic material and I can define something called an easy axis of magnetization and a hard axis of magnetization. Do I have some pen? Yeah. So suppose if you take a magnetic material and apply a magnetic field H and you measure the magnetization for a ferromagnet as a function of applied magnetic field, you are familiar with the curve. This is called the hysteresis loop, right? So this is a hysteresis loop of a ferromagnet that you are all familiar with. You apply sufficient magnetic field, all magnetic moments align in the direction of the applied field. And when you start removing this magnetic field, the magnetization gets reduced. And at a particular field in the opposite direction, the magnetization reverses from one direction to the other direction, and you get this hysteresis loop, right? This is for a conventional ferromagnet. Now I'm going to refine this ferromagnet to, for example, this is a single crystal ferromagnet, right? So everything is a single crystalline material. I can define something more. I can say that there is an easy axis of magnetization here and a hard axis of magnetization. Easy axis of magnetization, the name suggests it is easy to magnetize a material along the easy axis. Hard axis of magnetization means it's hard to magnetize a material along the hard axis. Now if I take this ferromagnet and apply a magnetic field along the easy axis, and then if I look at the hysteresis loop, the same hysteresis loop, the magnetization is here. Now even if I remove the magnetic field, bring it back to zero, still I have 100% magnetization. The remanence is 100%. Now if I increase the magnetic field in the opposite direction, you see that at coercive field, the magnetization switches from one side to the other side abruptly. The fully magnetization is changing to 100% this way, and you get a square hysteresis loop. Now on the other hand, if I apply a magnetic field along the hard axis direction, as I start increasing this magnetic field, more and more magnetic moments get aligned in the direction of the applied field, and above a critical field, all magnetic moments are aligned in the direction of the applied field, then there is no further enhancement of magnetization. Now on the other hand, if you start reducing this magnetic field, below this critical field, this individual magnetic moments will tend to go back to the original direction, and when I have the zero magnetic field, along that direction there is no net magnetization, because all the magnetic moments have gone in this direction. The component of magnetization in this direction is zero. Now on the other hand, if you start increasing the negative direction, again I get a straight line, and it starts saturating. So this saturation magnetization is same as this saturation magnetization. Now this particular thing I will use for sensor application, and this particular thing I will use for memory application. Now you may ask a question, why in your textbooks you haven't, forgive my drawing capability, it's not symmetric, it should be symmetric in every respect. Along about this axis and about this axis, it should be symmetric. This is what you see in your textbook. You may ask the question, then why this is different from that? In fact, both are same, because when you see this hysteresis loop, this is from a collection of particles, millions of particles. There are many of them oriented along the easy axis. There are many of them oriented along the hard axis, and there are many of them oriented in the intermediate direction. If you sum total all these things together, this plus every intermediate state, it will come close to this. That's how the hysteresis loop you see. Now I said that, look, when you switch the magnetization from here to here, it changes abruptly from plus 100% to minus 100%. That means if this is a magnet and this is a north pole, the question is that when I switch the magnetization, so what happens? You mark this as north pole and this as south pole, bring it inside a magnetic pole piece whose magnitude is higher than the coercive field, then the magnetization, when you take this thing out, you will see what you marked as north pole has become south pole, and what you marked as south pole has become north pole. Now the question is that how this magnetization reversal happens. It's not the magnet is rotating like this. What's happening is that the individual magnetic moments, small units inside, is switching the magnetization. Now the question is that, is it that everybody switches the magnetization like this, or some other process is happening? Just for you to have an understanding on that, let me just show you a simulation. This simulation is from a magnetic wire whose length is 500 nanometer, the width is 50 nanometer, and the thickness is 20 nanometer. Each of this arrow, which you see here, which is now pointed in this direction, is 5 nanometer by 5 nanometer by 5 nanometer cube. And these arrows are pointing in this direction, and this is magnetized in that direction. Now what I will do, I will apply a saturation field in this direction, and I start reducing this magnetic field, and then you will see here a line will come here, the hysteresis loop will come here. I start reducing this magnetization, magnetic field, and I will switch the magnetic field in the negative direction. I start increasing, then you will see that the hysteresis loop that will come in. And when the hysteresis loop comes in, you can also look at these arrows, what is going to happen to the individual arrows. There are two possibilities. All these arrows can rotate like this and go in the opposite direction, or something else can happen, right? So let me just show you what is happening, then you will understand. So now you see that the simulation has it started? Yeah, it started. So this magnetization field is now 0. Now I apply the field in the negative direction, starts increasing. You see something is happening at this corner, at that corner, and now the white color means it's a magnetic domain wall, and they travel against each other, and then the switching is happened. Now it is in that direction. Now I start reducing the magnetic field. Now it is 0 field, negative, positive direction. You see the arrow starts getting affected at these corners. A magnetic domain wall is formed here as well as there, and they travel against each other, and the magnetization happens. So if I take this magnet with the north pole and south pole, if I now apply the magnetic field in the opposite direction, first two magnetic domain walls gets nucleated at both the points, and these two magnetic domain walls starts moving against each other, and they merge together, and the magnetization reversal happens. That's how this is happening. This happens, everything happens within few nanoseconds, right? This is such a fast process. Now you may ask the question, why am I talking about these things? Where am I going to use it? Okay. Imagine that this is a magnet, right? And this is the north pole of this magnet, and this is the south pole of this magnet. Now I keep this magnet like this, and I say that when the north pole is towards you, I call this as a one state of this magnet. Just define state 1. And when the north pole is towards me, I call it as a 0 state. Now this is state 1, and this is state 2, state 0. Now imagine I have two such magnets, right? And I read from that side to this side. And what is the state? 1. And what is this?
0.
Now if I have two magnets, what is the state now? 1. And what is the state?
0.
And what is the state?
0.
So this is 2 bits of information, right? Now if I keep, can you see this? No, you can't see this. Let me see. Not large enough. Okay, let me just do something else. Okay, just see. Can you see this now? This is 1, 1. 1. 1, right? This is 4 bits. It's 1, 1, 1, 1. And what is this? What is this? This is? This is? Right? So now I have 8 pencils. So 8 bits here. Right? So there is a reason why I am keeping 8 bits here. What is 8 bits? 1 byte. So 1 byte represents a character. Right? For example, if I have sets of magnets like this, you can define zeros and ones depending upon whether the north pole is towards you or north pole is towards me. And now, if I take this thing and if I say that, okay, this is, if I put 0, 1, 0, 0, 0, 0, 0, 1, right? So it's now 0, 1, 0, 0, 0, 0, 1. When 8 has a property called magnetoresistance, that means the resistance of the material changes when you apply a magnetic field. Now if I have a magnet like this, there are magnetic lines of force outside, and this, if I bring this magnetoresistive material in this magnetic lines of force, the resistance of the material changes. The resistance of permalloy was changing at a rate of 4% per oersted. That means if there is 1 oersted of magnetic field there, and if I bring permalloy, it changes its resistance by 4%. Imagine if it had 100 ohm resistance, now on top of this, it changes the resistance from 100 ohms to 96 ohms. So that means 4% magnetoresistance. Now, as I make this magnet smaller, now instead of 1 oersted, you have only half oersted outside. If I bring the same permalloy, it will change from 100 to 98 ohms. And if I make it even half of that, 100 to 99 ohms. If I make it even half of that, 100 to 99.9 ohms. And similarly, if I make it smaller and smaller, the change in resistance of this permalloy becomes smaller and smaller. As physicists, we know that there is noise in every measurement. Now, if the magnetic field becomes sufficiently small, the change in resistance we are unable to measure. That's why you could not make the bit smaller and smaller. But now I'm going to talk about something called giant magnetoresistance. The name itself suggests the resistance changes in a large way. So that's why it's called giant magnetoresistance. And from 1998 onwards, our computer hard disk got giant magnetoresistance. That's why you could make the bit smaller and smaller and smaller, still able to find out whether it's a 1 state or a 0 state. So in a computer hard disk, we have a giant magnetoresistive read head. So when you try to read something, you hear a sound. Sound comes. That's because this magnetic read head is stationary here, and this disk rotates. In this circle, all the magnetic bits are aligned. So each bit is brought below this read head, and you read the information. It's a 0 or 1. Next bit 0 or 1. Next bit 0 or 1. Next bit 0 or 1. Like that, in this entire circle, you can read this information. And if this bit moves, if this read head moves slightly in, then the next track can be taken, and you can measure, find out zeros and ones. So by moving this linearly in and out, you can take the innermost track to the outermost track, and this disk nowadays rotates at a speed of 10,000 RPM, so 10,000 rotations per minute, right? At that speed, your hard disk is rotating, and the reading is happening during that time. So this is how precisely the information is read from your computer hard drive. And now, side by side to the hard drive, you have a write head. You must have all done this experiment where you take a screwdriver, wind a wire around it, connect to a battery, the screwdriver becomes magnetic, right? Now if you change the polarity of this battery, the magnetization reverses. Similarly, I have a yoke here, and this yoke has an opening here. Now I have a wire wound around that yoke. Now if I pass current, plus I current through this, that generates a magnetic field in one direction. And if I reverse this current, it generates magnetic field in the opposite direction. Now what's happening? Now I am bringing this yoke on top of this. I apply plus current. So that means the magnetic field is in my direction. So it switches in this direction. Now if I reverse the current, it switches back. So now each bit is brought below this writing head. And then you apply plus I current or minus I current. You write 0 and 1. And again, 8 such bits together gives you 1 byte and 1 character. So this is how precisely you write your information in your computer hard disk. That's why when you try to write information, you hear a sound. That sound is the rotating hard disk, 10,000 RPM. And then this right head is trying to write information, right? This is how you read and write information in your computer hard drive. So because of that, you see, if you look at the area density, gigabyte per square inch, you see that it starts increasing. Somewhere here, we have the first GMR head, Jan magnetoresistive head, got introduced in our computer hard disk. Now, because of that, what happened? This is the first IBM computer which was housed in a room much bigger than this hall, maybe 3 times, 4 times bigger than this hall. And it had a computer where the hard disk is with the 24-inch hard disk, 24-inch, 50 such hard disks together. All these disks need to be cooled, etc. And all these things together had a capacity of 5 megabyte, right? A computer which is 3 times, 4 times bigger than this hall was having a hard disk of 5 megabyte. Right now, if you look at, if you have 3.5-inch 2 such disks, you get now 12 terabytes. So that's the kind of hard disk which we have today, the state-of-art hard disk, right? So this has happened. See, from 5 megabyte to 12 terabyte, and people are not still happy. 12 terabyte is not sufficient. When I started doing when I did my MSc, the computer lab had a computer which never had a hard disk. So we bring our floppy. It's a 5-inch floppy. You insert it, you boot the computer, do all the programming, save everything in the floppy, and remove the floppy out. Then the computer is dead. There's no hard disk. And when I started doing my PhD, I got my first computer with a hard drive, which had 20 MB hard disk. Right? It's a big 20 MB computer, and 15 to 20 MB was used all the time. And when towards the end of my PhD, I got a computer which is 200 MB hard disk. And again, 150, 180 MB was used. Now even 2 TB computer says that hard disk is not sufficient. So our requirement is also going up. So people are also not happy with the current hard disk. But for the last few years, you might have noticed, there's no further progress, right? You get 1 or 2 TB hard disk for the last 2, 3, 4 years, and it's not increasing further. So the reason is that we have reached something called a super paramagnetic limit. So it's a fundamental problem. If I have a ferromagnet like this, and if I start reducing the size of this ferromagnet, below a critical size, this ferromagnet loses its ferromagnetic property. It becomes super paramagnetic. So super paramagnetic means I have an energy barrier, right? So this barrier height is proportional to the volume, the anisotropic constant of this bit. This is proportionality sign. Anisotropic constant times the volume of the particle. Now when the size of this particle becomes smaller and smaller and smaller, this barrier height becomes smaller and smaller. And now what happens, this barrier height becomes comparable to KBT, the room temperature. So that means if this is magnetized in this direction and this is magnetized in that direction, now without even applying a magnetic field, thermal energy is sufficient to switch the magnetization from one side to the other side. So that means when I look at this bit like this, it's one state. If I look at 0 state, it keeps fluctuating because the thermal energy is sufficient to overcome this barrier. So then people thought that, okay, so now you cannot reduce this volume any further because you have reached the super paramagnetic limit. Then so it's okay by the time it comes. So the idea is, in today's hard disk, we keep this barrier height as 60 times KBT to make sure that it has got some lifetime. So if the barrier height is close to KBT, that means the lifetime is low. So now you start increasing this KBT. You cannot increase the volume because your bit size, you don't want to make it big. But you develop new materials which has got higher anisotropic constant K. So as you increase the anisotropic constant, this barrier height also increases. Now the current hard disks are designed to have 60 times KBT so that it gives a lifetime of 10 years. So whatever you are writing in your computer hard disk, statistically stays there for a duration of 10 years. So after that, the information is lost because of this thermal fluctuation. Now the point is that you cannot keep on increasing this KBT. That means if you start increasing this, that means the field that is required to switch the magnetization also goes up. So that means when you do the writing, you need larger and larger field to switch the magnetization. So I can increase this lifetime from 10 years to 100 years. But for each writing you need much more magnetic field, so that there's a consensus in the community that I don't want to apply very large field and I don't want to have very small lifetime. That's why the compromise is that 10 years of lifetime with a moderate magnetic field. That's how we reach this particular number. So now we have reached this something called the super paramagnetic limit. Because of that, in the last few years we don't have much improvement. Then people thought that how to circumvent this problem, right? So the real estate in the computer hard drive is becoming very expensive. So then we follow the normal real estate business, go vertical, right? So in a village you can have a big plot in which you have a palatial house. Now if you come to Bangalore, you see everything goes vertically up. Then similarly people thought in the computer hard drive also, you start making the bits instead of lying like this, perpendicular. So this is an in-plane magnetized state. Now you make material which is perpendicularly magnetized. So now when the magnetization is upward, you call it as a one state. When the magnetization is downward, it's called it as a zero state. Now you can have up and down situation, and people are now successful in making this diameter down to 4 nanometers. So 4 nanometers means take your hair, vertically split now 20,000 times, and take one piece out of it, that is 4 nanometers. That means now at your hair, dimension of your hair, you can have 20,000 such bits, right? That's how you reach this. So that's why people go into perpendicular magnetic recording. This is one example of that. Here you see, black dot means it's magnetized towards you, white dot means it's magnetized into the board. So this I call it as 1 0 1 0 0 0 0 0 0, then 0 1 1 0 1, like that, right? And now the diameter of this is gone down to 4, and the next target is to go to 2 nanometers. That means you have 40,000 times 40,000 bits sit in your hair. So now all this happened. Okay, maybe I will just show you that picture. I should have copied it here. So this is the perpendicular magnetic recording. That's a read head as such. And now this is the right head. Now you look at the right head geometry, it has changed. Look at here, there's a yoke. Here it is very wide, where here it is very narrow. Now the magnetic lines of force which goes from there to here. Now since this is very narrow, the density of that is very high. And this is very wide, the density is low. So whatever is coming below this yoke gets magnetized in that way or that way. So that's how the writing is happening in this kind of hard disk. So now all these things happen because of something called giant magnetoresistance, which some of you are familiar with. So the name itself suggests the resistance changes. Suppose, so here you take 30 angstroms of iron and 9 angstroms of chromium, and then make a multilayer of 60 times. Then you get, if you look at the magnetization, the resistance as a function of applied field, the resistance changes by 50%. Permalloy had only 4%, now it is 50%. Now if I take iron alone, it won't give you any magnetoresistance. If you take chromium alone, it won't give any magnetoresistance. Most of us will abandon both the materials, right? But these people, they thought that there is something more can happen. So they took iron and chromium, which is two materials that was not showing any magnetoresistance. They made a multilayer out of it, and then one group by Albert Fert in France, the second group by Peter Grunberg in Germany, they made this kind of structures and discovered giant magnetoresistance. And this was discovered somewhere in 1986-87. And in 1998, it came to our hard disk. And in 2007, they got the Nobel Prize in Physics for the discovery of giant magnetoresistance, right? So now it's a fashion. Something which is not, nowadays people take two insulators, bring them together, and the interface of that they get metallicity. And you take two insulators like lanthanum lanthanum titanium, strontium titanium oxide and lanthanum aluminum oxide, two very, very strong insulators. At the interface, people now start seeing superconductivity. You take two non-ferromagnetic materials, at the interface, people start seeing ferromagnetism. So all this is coming from this thing. So you take two materials that will never have a property of something, and you join them together at the interface, the property changes, right? So for that reason, they got the Nobel Prize. So this is for the physics students. Let me just explain. You know about the band structure, and when it comes to a ferromagnetic material, you can also have spin-resolved band structure. So upspin electrons and downspin electrons will have two different band structures. So if you have a paramagnetic material, the upspin and downspin electrons are equal in number. So the density of states at the Fermi level for the upspin electron and downspin electron is equal. But when it comes to a ferromagnetic material, the density of states for the upspin electron is different than the density of states for the downspin electron. That means you have a majority electron and a minority electron. And when it comes to the other extreme, which is a half metallic ferromagnet, for one Fermi level, so that means it's a metallic nature, whereas for the other type of electron, you see a band gap. So now what happens if I pass 100 electrons through this material, 50 upspin electrons, 50 downspin electrons. For only 50 upspin electrons, it's metallic, it passes through. For the 50 downspin electrons, it's an insulator, it won't pass through. So you get something called spin polarization. So this kind of effect is used in the magnetoresistance. What happens? An electron, so it is like two ferromagnetic layers separated by a non-ferromagnetic layer. A majority electron from here comes to the other side, whereas a majority electron, when they are magnetized opposite to each other, a majority electrons will not have sufficient place to sit there, so then there won't be any transmission. So that means, to get some more ideas, two ferromagnetic layers separated by a non-ferromagnetic metallic layer. Now when the magnetization of both the ferromagnets are parallel, you are passing 100 electrons, 50 upspin, 50 downspin. This electron is compatible to this ferromagnet that passes through. Non-ferromagnetic metallic layer, there's no preference. It comes to the next layer. Again, the spin and the magnetizations are compatible, that passes through. That means 50% of the electrons pass through. Whereas when you take this minority electron compared to this, it gets scattered a lot in this layer because there's no density of states are very less. And it gets scattered even further. That means when I put 100 electrons, only 50 electrons, this is just numbers I'm throwing, 50 electrons come out. Now when the magnetic moments are anti-parallel, look at for this pin, this moment is not compatible, they get scattered there. Now for this pin, this moment is compatible, it passes through that layer. But when it comes to the second layer, it again gets scattered. So effectively, no electron come out. So more scattering means more resistance. Less scattering means less resistance. So here you have less scattering compared to that. So by making these two ferromagnets parallel, you have a low scattering process, that means low resistance. When you make them anti-parallel, more scattering, high resistance state. So this is how you, by applying a magnetic field, you can make them parallel or anti-parallel. That's how you go from a low resistance state to a high resistance state. You can get 50% change in the resistance. That's how you get giant magnetoresistance here. This is similar to the optics experiment you do. You pass light through a polarizer and you keep another polarizer, which is exactly with the same optic axis. You see light comes out. Now if I switch the polarizer by 90 degree, then this light is blocked by the second polarizer. So now this is like a valve, right? You pass light, close light, pass light, close light. Similarly, this is for spins of the electrons. It's like called spin valve. When the magnetizations are parallel, electrons pass through. When the magnetizations are anti-parallel, it won't pass through. Same as the optics experiment. That's why it is known as spin valve, and that's why it's spintronics. If the electron didn't have a spin, this effect won't be there. So this is why it is called spin-based electronics or spintronics. Now the real challenge in this spin valve research is this. This burger, if you take the burger bun, you'll see the sauce there, right? So this is a precise problem the experimental physicists face. When you make these metallic multi-layers, they intermix. When they start intermixing, the properties are getting lowered. So now our job is to make a burger where the sauce is not getting into the bun. So that means atomically flat interfaces without intermixing. That's the experimental challenge all of us are facing at this point of time. With this, let me just introduce one more small concept, something called tunnel magnetoresistance, right? Here, two ferromagnetic layers separated by a thin insulating layer. In the previous case, two ferromagnetic layers separated by a thin metallic layer, right? So this is, okay, let me ask a question. How many of you are using tunnel magnetoresistance here? Anybody? Okay, I have to rephrase the question. How many of you are using a computer which is made after 2005? Right? So the good news is that all of you are using tunnel magnetoresistance. Now let us see where we are using. So here what happens, when the two ferromagnetic layers are aligned parallel, electrons can tunnel from one side to the other side. So this is like this movie where a man is running towards a wall. He diffuses through the wall and running from the other side, right? So if I go there, I will be stopped because I'm a classical object. For an electron, when the barrier width is very, very, very small, electron can tunnel from one side to the other side. This is precisely the one-dimensional potential barrier problem we study in quantum mechanics. Precisely that. So now what happens? The electrons tunnel from one side to the other side. Now when the magnetizations are parallel, more electrons tunnel. When the magnetizations are anti-parallel, less electrons tunnel. When more electrons tunnel, low resistance, high current state. When less electrons tunnel, low current, high resistance state. Now by making this material parallel, I can have a low resistance state, and making them anti-parallel, I can have a high resistance state. No? So the magnetic field can change the magnetization direction. That can change the resistance. So there is again a magnetoresistance as same as the previous one, but now additionally there is tunneling. That's why it is called tunnel magnetoresistance, right? So the tunnel magnetoresistance, yeah, I think many of you know Jagdish Mudera. So yeah, so he has shown this way back in 1995. Two ferromagnetic layers separated by a thin insulating layer. When the magnetizations are anti-parallel, the resistance is high. When the magnetizations are parallel, the resistance is very low. And presently, we have a TMR of 500% observed. And this is how the tunnel current falls. So as you increase the insulator width, the resistance and the current drops. So that's why you need to have an extremely thin tunnel barrier. Then only the electrons can tunnel. And when it becomes extremely thin, then it should be perfect. Otherwise, this electrode will start shorting with the second electrode. So the challenge is that to make extremely thin tunnel barrier and very perfect tunnel barrier, then only you get tunnel magnetoresistance. Physics is again same. Two ferromagnetic layers separated by an insulating layer. Now, this is the majority electrons in one ferromagnet. When the magnetizations are parallel, these electrons can tunnel from here to here, enough density of state, so more electrons can tunnel. So more electrons tunnel means more current. You have a potential difference, more electrons tunnel. That means for the same potential difference, you have more current. More current, same voltage, less resistance. Now when the magnetizations are anti-parallel, now the majority electron here has become a minority here, and a minority electron has become majority here. Now there are large number of red electrons. I mean, electrons are not red or blue. This is just for your understanding. Magnetized in one direction, I refer it as red. Magnetized in the opposite direction, I call it as blue. So now the red electrons, large number of red electrons are there, but there's not enough state for them. Small number of blue electrons here, but large number of states. Doesn't matter. You can't go because the guy who are large in number have no place to sit there. The guy who has got large states there cannot go there because I don't have. So in effect, less electrons tunnel. Less electron tunnel means higher resistance state for the same voltage. So that's how you get high resistance or low resistance. I bring back my roadmap. You see here, somewhere here, we started introducing the TMR, tunnel magnetoresistive read head. That's why I asked you the question. The computers which are made after 2005 uses the same concept of tunnel magnetoresistance. For the MSc students sitting here, this is exactly the same problem. You must have studied this tunnel effect. electrons come with a wave function, tunnel through the potential barrier, and then comes to the other side and again goes. This is a wave function. So this is exactly same problem what you study as. So you may ask the question, when I study quantum mechanics, where do I use it? Every day you are using in your computer. It's a one-dimensional potential barrier problem. So now with one more small concept, I wind up this lecture, which is magnetic random access memory, which is used from the tunnel magnetoresistance. Let me ask a question. How many of you are using magnetic random access memory? Raise your hands. Let me see. Raise your hand. Let me see. Okay. The point is that we are not using it. But if I give this lecture after 2 years here, again I think I will ask everybody to raise the hand, right? So now let us take this concept. Two ferromagnetic layers separated by a thin insulating layer. Now when the magnetizations are parallel, I have a low resistance state. When the magnetizations are anti-parallel, I have a high resistance state. So now that itself I can use as a memory. When I say low resistance state, I call this as a zero state. When I have a high resistance state, I can call it as a one state. Now if I make a trilayer structure, just by measuring the resistance, I know it's a one state or a zero state, right? So now if I take a 12-inch wafer, I deposit one ferromagnetic layer and another insulating layer, another ferromagnetic layer. This trilayer stack is a memory element, but that's on a 12-inch wafer. So where I cannot use it that way. So now I become a carpenter. I just carve structures. Imagine that this room was a wafer and all of you are joined together at time t equal to 0. That means all your legs are joined, all your bodies are joined, all your heads are joined. You are a single entity. Me as a carpenter comes and remove material around the person. So now I created this structure. Head is there, body is there, leg is there. Now I come and remove material around. I have head, body, leg. So like that I go around and carve the structure. So what I do something called a lithographic process and I make this individual structure. Now this individual structure is one bit. So the head and the leg, I will say magnetized parallel or anti-parallel is 0 or 1 state. I can have it low resistance, high. So similarly, I now carve so many structures inside this room and individuals are individual bit. Now, how do I write and read information? I have some more things. I connect a copper strip which connecting all the legs. I connect another copper strip that connect all the heads, right? Now this is the structure, right? So now all of you, individuals are this, stepping onto a copper wire, and all your heads are connected by another copper wire. This is the structure. Now if I measure the resistance between this point and that point, I get the resistance of this stack. If I measure the resistance between this point and this point, I measure the resistance of that. Now I measure the resistance of ith row, jth column. I find out the resistance of the ith row, jth column person. I don't have to go there to find out whether it's a 0 state or 1 state. You see in the computer hard disk, each bit had to come below. There's a rotation, 10,000 RPM. Now I don't move. I just connect two lines, ith row, jth column. I know whether it's a 0 state or a 1 state. So I want to find out the state of that person. I connect that wire and this wire. Then I know the resistance of that person. Now, without moving to a location, I'm able to read this information back. Right? Similarly, now how do I write the information? Either I can have this right head going to everybody's head and applying a magnetic field and switching. Or now, I can pass current through this line. If I pass current through this line, imagine that your head is connected to this copper wire and I'm passing current through that. When I have sufficient current, there is a magnetic field generated, right? Current carrying conductor has got a magnetic field. When this magnetic field is higher than the coercivity of the ferromagnet, it switches. But the problem here is that if I pass sufficient current, everybody's head turns into the opposite direction. That means everybody in this line switches, which I don't want. I want only one person to switch. Now the trick is, you pass 50% current through this. So I pass 50% current through this, nothing happens to anybody because magnetic field is not sufficient to switch the magnetization. Now imagine another line is there, I pass 50% current through that. So that also creates a magnetic field. This also creates a magnetic field. At the junction, these two magnetic fields superimpose. So now, ith row, jth column, I can pass current through the ith row and the jth column, and the junction, you will have this magnetic field superimposed, it switches the magnetization. So I can write now 0 or 1 without going to a location. I can just pass current through this. And I want to switch the magnetization from one direction to the other direction, reverse the current. So now, without going to a location, I can now write information or I can read information, right? So this is called magnetic random access memory. So this is what I was telling. There's a current carrying conductor, generates a magnetic field. Another current carrying conductor generates a magnetic field. At this junction, the magnetic field superimposed, and that is sufficient to switch the magnetization from 0 state or 1 state. In reality, every of this, I mean, it's very easy to say that, I curve this and all, but in reality, it's much more complex. A transistor is kept below every bit. When the transistor is on, current can pass through this, and this is a reading process. When the transistor is off, I can pass current through these lines. That's the write process. That's how you read or write information in your computer, in this magnetic random access memory. So this transparency will tell about everything. Currently, you have RAM in your computer, right? So that RAM is non-volatile. It's volatile. That means you need a battery backup to keep the information in your RAM. The moment battery is removed, information is lost. That's why when you switch on the computer, you have to go through a boot up sequence, right? It's time-consuming boot up sequence. Whereas MRAM, magnetic random access memory, is non-volatile. Means once I switch the magnetization in one direction, unless somebody comes and put a magnetic field there, that information is there always. That means it's not a volatile memory. Whereas in our computers, the RAM is volatile. Unless the battery backup is there, the information is not there. Now somebody made a calculation in 2000, 2010 or so, how much power we are consuming in our RAM. Interestingly, it is equivalent to several nuclear power plants. Because each one we may use only 2 watts of power. But maybe 1 million computers around this location. Imagine integrate all over the world. It's equivalent to several nuclear power plants. So if you can just replace your RAM of your computer with a non-volatile memory, the power that you're going to save is enormous. And write time, DRAM is 50 nanoseconds, MRAM comparable, read time comparable. So now you can read and write at the same speed as your RAM. And it is non-volatile. So imagine this RAM is needed in your missile heads and all, right? In the missile head, you cannot have the conventional DRAM. You cannot go and check whether the battery is working every day, right? So you need non-volatile memory. So earlier, non-volatile memories were costing $1 per bit. So that means if you want 1 megabyte in your missile head, you need $1 million for RAM alone, right? So that's the difference. Now the read method is destructive. In a DRAM, this is like this. Okay. Let me just finish this. Empty bottle, full bottle. I can define a memory now. When the bottle is full, it's a 1 state. Empty, 0 state. Right? Now if you give me 10 bottles, 8 bottles, I'll give you 8 bits. Right? 0 state, 1 state. So I keep all the 8 bottles. First one full, next as 6 empty, 7th one full, it's a 1 0 0 0 0 1 is A. Similarly with this is a memory again. Now in this one, imagine this were opaque bottles. How do I know that this is full or empty? I open, pour water out. If water is coming out, I know water was there, so it's a state 1. When I pour water out, no water is coming out, then I know it's a 0 state. Now once I start pouring water out, then I have, it's a destructive method. Now what I do, I'll pour all the water out, keep the bottle, fill everything and keep it back. Otherwise my state 1 will change. This is what is happening in your DRAM in the computer. Instead of water inside, it's an electronic circuit where charge is stored. You try to discharge, if there's no discharge current, it's empty, 0 state. When you try to discharge, Is discharge current is there, it's a one state, because charge is coming, it's a one state. So after discharging, you charge it back and keep it. So that's how you keep ones. So the read method in DRAM is destructive, whereas MRAM, no, you just measure the resistance. That won't change anything, right? Now you have 10 power 15 rewrite cycles in both cases. Here the operating current is 100 milliamps. Now in MRAM is 10 milliamps, but the latest technology, which is not going to use any more magnetic fields to generate. See, earlier days you needed magnetic field to switch the magnetization of a material. Now we can switch the magnetization without magnetic field. By electrical current, we can switch magnetization of a material, right? This is called the spin transfer torque mechanism. There this number goes a gain factor of 10 down. Now for operation 100 milliamps, where is this 100 milliampere is going? 90% of that is going, or 99% of that is going in heating stuff. So the heating is a big problem in all these electronic circuits. So now the next generation devices will have low power consumption. See, now Google has started a station in Antarctica, right? Their data for consumer market, so that hopefully the MRAMs will come to our computer hard drive. So that means when you switch on the computer, it's on, right? There's no boot up sequence. And your mobile phones, right? You know, now 128 GB mobile phone. Imagine that entire 128 GB is becoming in a RAM, right? How fast your computers will, how fast your mobile phones will be. Imagine the computer, now hard disk is going away and it becomes RAM. The entire hard disk, 2 TB RAM, how will it be? So fast, right? You write information. Suppose now if you want to write 100 megabyte file into something, you take some time to write or read. Whereas with this kind of concept, so writing time is nanosecond, reading time is nanosecond. So that means, 1 gigabyte is also can be written in 1 second. So that will be the progress that's going to happen. Yeah. With this, let me just stop at this point of time, and if you have questions, I am happy to answer. Thank you. Any questions from the students?
Let me ask one question.
Sure.
At present, the computers are available with hard disk,
Yeah.
the normal mechanical.
Yeah.
And also they say SSD, solid state drives.
Yes.
To which category it belongs, solid state drives? Which kind of RAM is it?
No, that is close to the DRAM kind of a thing. Yeah, it's a solid state. Yeah, again,
It has not come to this.
not come. See, the difference is that it is not as fast as RAM.
Yeah.
Solid state drives, I mean, you may think it is fast as RAM, but it is not. It is orders of magnitude slower than the RAM. It has not reached the speed of the RAM. Plus the endurance is very low. See, the thing is that people who are savvy about this thing won't even wait for the lifetime. We will throw away this when the next model comes. So you don't know the lifetime. Whereas the computer hard drive which you had 20 years back, still it works, right? But SSD, I don't think its lifetime is that much. But it is not a RAM. It's not. I mean, they say it's a solid state drive. It's faster than our computer hard disk. That's it. But no way near our RAM.
More than 190 when the idea of spin was introduced, I think by Samuel Goudsmith and
Yeah, Uhlenbeck and Goldsmith.
I
Yeah.
don't think they ever they dreamt that you could give
Oh,
rise
that's-
to
Yeah.
a branch of electronics called as
That's a very
Spintronics.
interesting story, When Uhlenbeck and Goldsmith thought, first they found that the electron has got a magnetic moment. So you have to find a reason why electronic has a magnetic moment. Then they thought that the electron is rotating in this direction, then you have upspin, rotating in the opposite direction, it is a downspin. That's what they theorized. Then they wrote the paper and sent it on those days by sea mail. By the time this paper reached the editorial office, these people realized what they have said is wrong. Because if the electron has to rotate, it has to rotate 137 times faster than light to get the same magnetic moment. So they immediately wrote the next paper saying that what we have said is wrong, please withdraw the paper. By the time this reached there, the paper got published. So that's why the word spin came, but still, that is in our mind. The concept is not due to that. It's not rotating electrons, but still we use the same concept to teach students that, rotates clockwise, anti-clockwise, up spin, down spin.
Rather than say spinning electron,
Yeah.
we say it as electron spin or intrinsic spin.
Intrinsic. See, we have mass of the electron, right? You don't ask a question from where the mass is coming. Electron has got a charge. You don't ask a question where charge is coming. Similarly, it's the fundamental right of the electron to have a spin, a magnetic moment.
It's born with the mass.
Yes. Born with the
Like
charge. Born with the spin. Right.
It is as if you are able to measure a particular property associated with the particle.
Yes, exactly.
And then you imply.
Yes, exactly.
This is how we generate.
Exactly.
And I may remind one small thing, as you said. Now Spintronics has taken off. When laser was invented, nobody knew
Yeah.
where it could be applied.
Yes.
Now it is applicable everywhere, whether it is in surveying or surgery or in communication.
Yeah.
Like that, the sky is the limit, as you said. Where will it take us?
Yeah, see, the thing is that if you look at transistor,
Yeah.
invention of transistor, invention of laser, these are the milestones in physics. Right?
This is almost.
So here also, see, Spintronics is taking interesting spin now again. Initially, you had ferromagnetic materials, you apply magnetic field to control.
Yes.
Next generation Spintronics, ferromagnetic material, electrical current to switch the magnetization. Next generation Spintronics won't require even ferromagnet. With the material with a high spin-orbit interaction with the electrical current, you will have Spintronics. So that's how things are going. Now with this spin memory, spin FET, things will, go much more.
In 1975, there was an article written by George Uhlenbach and Samuel Gauss-Schmidt
Yeah.
in Scientific American,
Uh-huh.
titled 50 Years of Spin,
Yeah.
in which they had lamented that they were not given that recognition,
Yeah.
although they had given an idea which could really bring about a revolution in the field of quantum mechanics. And I think the idea actually deserved a Nobel Prize, but they were not given.
Yeah, that's correct. Yeah.
What could be the reason for this?
idea.
Although
Yeah.
people like the experiment that they did to
Yeah.
verify the idea of spin, they were given the Nobel Prize.
No,
but not this.
what I understood was when Goldsmith and Uhlenbeck conceived this idea, parallelly there was I forget this name, there's an American scientist who also conceived the same idea, but he immediately calculated and realized the flaw in that one. So probably that could be the reasons. And interestingly, the Stern-Gerlach experiment, right?
Yes.
Now we talk about spin discovered by Stern-Gerlach, but Stern and Gerlach never said spin. They did the experiment, but they did not. Their idea was to talk about orbital angular momentum, but they never discovered spin. Now, later on, people said that what they found was spin. Actually, they never said, actually, these two guys, Stern and Gerlach, the professor and the student did a lot of experiments and they didn't get anything, so he was going back. And when he was in the railway station, there was a pilot strike, the loco pilot strike, so he couldn't go home. So he came back. Then asked the professor what to do. He said, okay, go and continue the experiment. So he continued the experiment, and it's a very interesting story. So they were working with the silver, right? So then nothing was there. So then the professor had a habit of smoking cigar. So this plate was here, nothing is there. So after some time, you see the two black spots coming. That is because the cigar had the sulfur. The sulfur was reacting with silver, and that was giving you the two spots. And this experiment was enacted. People tried to put sulfur and it never worked. Only the cigar's fume works. This is how they discovered there are two spots. And that time also they didn't realize that it is due to the spin. This interpretation came much later. So because of that loco pilot strike, and then the cigar, Stern and Gerlach experiment has become a famous experiment. Okay, these are all interesting histories. Okay, I think there are no more questions. Thank you for your attention.
For his talk, I think most of us are able to at least
getting a gist of what is Spintronics is. We profusely thank him for his talk. I may be reminded of one small thing in the context of what Professor Anil Kumar said. He went on explaining when Einstein conducted photoelectric effect, tried to analyze the photoelectric process, he said the electron is emitted instantaneously. Then in the next century, people went on perfecting the measurement of the time interval, came to femtosecond, attosecond, so on. Quite often, I feel it is well worth pondering over even the old experiments. At some place, now I have forgotten the details. We teach kinetic theory of gases in PUC or in degree classes. We say, we imagine a box, a molecule moves in a particular direction, strikes the wall, comes back immediately. And I read somewhere, it doesn't come back immediately, it oscillates more than 25,000 times before it comes back. When it strikes the wall and comes back, it is not as if you normally see a billiard ball striking.
We can draw for answers from the topic.
Right? The electron has got a spin. You can measure, you will find out when the magnetic and your
Doesn't come back immediately,